Hello and welcome to our IROS conference paper entitled Learning-Based Adaptive Admittance Controller for Efficient and Safe pHRI in Contact-Rich Manufacturing Tasks. We divide a pHRI task into distinct subtasks. We then develop a learning-based adaptive admittance controller using subtask detection and motion estimation to minimize human effort when driving the robot in space and prevent instabilities when in contact with stiff and rigid materials. Each subtask requires a different interaction behavior in many pHRI tasks, such as drilling, polishing, and cutting. During driving, for example, we need a smooth interaction to minimize human effort, while during contact, we require higher stability. We consider a collaborative drilling task in 3D space. Here, the interaction force resulting from the human and the workpiece is sent to the admittance controller, which returns the reference velocity to be tracked by the robot. Relevant signals are sent to the subtask detector and motion estimator, which together adapt the damping parameter of the admittance controller. We perform 2 sets of pHRI experiments with a robot. Spring compression experiments are conducted in virtual environments to collect data under various conditions efficiently. After training and validating learning-based models, we then test the trained model in real drilling experiments to evaluate their real-life performance. The task starts with a medium admittance damping value, which is adapted to a low value as soon as driving is detected by the subtask detector. Motion progress is tracked during driving, and once estimated progress reaches a threshold value, marking the imminence of contact. Damping is adapted to a high value to prevent instabilities at contact. The subtask detector is active throughout the task. It is an LSTM model that takes downsampled sliding windows of magnitudes of human force, interaction force, and Cartesian velocity, and returns a categorical prediction of the current subtask. Accuracy and F1 score are used as its performance metrics. The motion estimator is only active during driving. It is a 1D CNN model that takes sliding windows of magnitudes of Cartesian velocity and acceleration and returns the instantaneous motion progress. RMSE and R-squared values are used as performance metrics. We perform virtual spring compression experiments with the robot to collect a rich dataset for training. 5 subjects perform the task with various target positions and sizes while repeating each condition 5 times. Adaptation is based on hard-coded subtask detection only. K-fold cross-validation is performed by keeping one subject, distance, location, or target size for testing and using the rest for training. As can be seen, both the subtask detector and the motion estimator achieve near-perfect test set performance statistics, which denotes high generalization capacity for the models. We then deploy the trained models on the adaptive control system and conduct online testing experiments with 3 controllers: 1 fixed controller, 1 adaptive controller with subtask detection only, and 1 with subtask detection and motion estimation. We also examine task performance metrics such as human velocity, force, and effort during driving, as well as oscillation amplitudes at contact. Even though the trained models are tested under new circumstances, both models achieve adequate performances. According to the subtask detection confusion matrix and the motion estimation regression performance seen here. As seen in the task execution metrics reported here, average force, average velocity, and total human effort were significantly better during driving under adaptive controllers C2 and C3 compared to the fixed controller C1. Furthermore, oscillation amplitudes at contact were much smaller under C3, which used both subtask detection and motion estimation, compared to C2, which only used subtask detection. Finally, we deploy the trained models in a real drilling task in Experiment C under similar conditions to those in Experiment B to compare their real-life online performance under adaptive controller C3, which uses both subtask detection and motion estimation. Performances reported here are similar to those reported in Experiment B, indicating that model performances do not drop in real experiments and remain acceptable for real-life tasks, further denoting the generalizability of the models. In conclusion, we divide a pHRI task into subtasks and train a subtask detector and motion estimator to adapt the controller such that human effort is minimized during driving and instabilities are prevented at contact. Future ideas include using combined subtask detection and motion estimation for shared autonomy, kinesthetic teaching, or transfer learning to further boost productivity and enhance human-robot interaction. Thank you for your time.